Series resistors and voltage division. The key things to remember about circuit elements in series is that the current through each device is the same, and the sum of each voltage drop across each device must equal the applied voltage to the stack of devices. So mathematically, I equals I R1, which is the current through R1, equals I R2, which is the current through R2, and I R3, which is the current through resistance 3. And these voltages, VC and VBC plus VAB, has to sum to the applied voltage. And notice that when a voltage is referenced to ground, you don't need to put a comma ground after it. So VA is measured to ground, but VAB is measured across that resistor. VBC measured across this resistor. And VC ground measured across this resistor is still referencing voltage C to ground, so we don't need the comma ground. Let's find the current and each node voltage. Here we have our relationship where the current through each device equals each other, and that the sum of the voltage drops equal the applied voltage drop. We have Ohm's law, V equals IR, and we can rewrite this to V applied equals I times R total. And we remember that the equivalent resistance of a series connected resistance stack is just the sum of those resistances. So if R total equals R1 plus R2, R3, and I solve for the current, I get 0.3 milliamps. And when I substitute this into I times R1, which is the voltage drop across AB, I get 3 volts. And you can see that I get 3 volts across R2 and 3 volts across R3. And you'll notice that when the resistances are the same, the voltage drops are the same in a series connected. I could have 10, 20, 32 resistances in this stack, and if they were all the same, the voltage drops would be all the same. This can help with intuitive circuit design later. Now I just want to call your attention to something for later. The current through each device is the same in series connected circuits, and the sum of each voltage drop across each device must equal the applied voltage to the stack of devices. The reason why I'm using the word devices and not just resistors is that this is true for everything. Resistances, capacitance, inductances, diodes, transistors, and op amps, if they are connected in series, the current is the same, and the voltage drop across each one has to sum to the original applied voltages. Now granted, capacitances, inductors, capacitances are open circuit at DC, and inductors are effectively a short circuit at DC, and so these become important with frequency. It's true that diodes are nonlinear, where I does not equal, where voltage does not equal IR, but we can find that small regions where it does. Same thing with transistors. Op amps take a little more analysis, but whenever you see things in series, these two relationships will apply. And rather than talk about resistance with these kinds of devices, we can use the term impedance. Now, here's a question. In the previous example, VA equaled I times R total. And it might seem, why have 3 resistances that you only add to find the total current and the voltage drop? Why not just use one resistor? And the reason is that resistor networks like this can be used to create voltage references. For example, if I want a system to show 3 levels of temperature, just right, temperatures below 99 degrees Fahrenheit, I want a green LED to be on. If the temperature is above 99 degrees, I want the green LED off and the yellow LED on and a red LED off. And if I'm above 104, I still want the green off. The LED that's yellow can be on, and then the red LED is on.